Hi, my name is Maria,
And I'm Grant Gallagher.
and today we'll be talking about relative motion, specifically rotation about the center of mass of a rigid body. First, let's quickly go over some definitions. What is the center of mass? The center of mass of a rigid body is a position on a rigid body where the weight is evenly distributed in all directions. You can consider the center of mass as a point where the mass of the body is concentrated. Now, what's relative motion? Relative motion is a calculation of the motion of an object with regard to some other moving object. As you can see in the picture, relative to the woman on the train, the trees and the bridge are moving past her. However, in reality, the tree and the bridge are stationary, and she is the one who's moving.
So how do these terms coincide with rotation? Depending on the reference frame, we can view the movement of an object in two separate but equally valid ways. In the first way, you can consider an object translating, but it's also rotating about its center of mass. This means that as it's moved, everything on that body is rotating about its center of mass. Another way you could view this is that an object is in pure rotation about a specific point, and that is not translating, called the instantaneous radius of curvature. As seen on the diagram on the left, you can consider this body to be translating about its center of mass while also rotating as it's moving. Or you can consider this body to be in pure rotation about a point that is off of the rigid body. As seen in the diagram on the right, you can see that the object first translates about its center of mass, and then it rotates about one of its ends.
Okay, so for our experiment, we decided to prove this by throwing a tennis racket in a projectile motion while it's also rotating. Go. Okay, so as you can see, it's hard to visualize this behavior under normal circumstances. We decided to find another way to more clearly demonstrate this behavior. First, we found the center of mass of the racket and attached the white LED to its position. We found the center of mass by balancing the racket on our fingertips. Then, we attached the red LED to a separate point on the body of the racket. Okay, so with the LEDs attached, we created a long exposure image which followed the path of each point during the projectile motion. We first started by following the path of the center of mass with the white LED. As you can see by the image, the center of mass follows a near perfect curvilinear path. We recreated the same throw, but this time with only the red LED on. As you can see in the picture, the point on the handle does not follow linear motion. In the third and final picture, we expose both points so you can see that the red LED follows a cycled motion as it rotates about the center of mass.
So what exactly is happening here? Here we have a picture of the tennis racket, and you can imagine that it's being thrown and also rotating. Now, I've drawn the center of mass and the point P on the tennis racket as you would see the LEDs. We can see that the red LED, or point P, is going to follow a circular path around the centroid. We can treat this similarly to a wheel or a disc that is moving in a translational pattern. As the center of mass, point G, moves to the left in a projectile motion, it's also accelerating downwards by gravity. At the same time, this tennis racket or disc is rotating about its center of mass. Since it's rotating, point P is going to have a normal acceleration and a tangential velocity. Now, when you consider this in addition to the translational velocity, the vectors are going to add. So the tangential velocity of point P and the translational velocity of point G is going to add, and the accelerations are also going to add. As you can see from the yellow arrows, this is the absolute velocity and acceleration at point P. You can solve for these components mathematically using relative velocity equations.